Hey, welcome back to Math with Patrick. Today is July 7th, and we're solving problem number 188 from the Daily Epsilon calendar. And we need to find the area of, I'm assuming, these three blue regions all added up. And we have quite the interesting diagram. It's a regular hexagon. It's like six-sided shape. Regular just means all six sides and all six angles look equal to each other. And as we kind of look at the other parts or other features of our hexagon, it seems like we have the Triforce from Zelda, where we're like cutting this triangle exactly in half or into four parts. So half along the side lengths or into fourths for the area. And then additionally, we have this tiny little Triforce within another larger Triforce. And I think this has the same idea of cutting side lengths in half and area in fourth. So that's actually something kind of cool to note. Like if I just call this blue area A, then this blue area should be A over 4. That's just because we have 4 equilateral triangles. All of them have to have the same area. Only one out of the 4 is shaded. And then this guy over here is going to be A over 16 because we have 1/4 of 1/4. So that's kind of cool. All of this, all added up, should be equal to 7 today. And maybe I'm debating if I want to like combine the fractions and get like one expression with A. Why not? Let's do it. We could find a common denominator. We'll do 16A plus 4A plus A over 16. Here is my A, this is A over 4, and then here's A over 16. We can add up all of those A's in the numerator. We get 21A over 16, and I'm hoping that this is equal to 7 today. So it looks like we need to use this value to somehow find the area of this triangle. And I'm assuming that it's this side length right here. So we should relate side lengths to areas of equilateral triangles. Well, let's just kind of take a look at an equilateral triangle. We'll just mark all of these sides with an S for now for side. And to find the area of any triangle, really, you just need to find a base times a height. And they have to be perpendicular to each other. Now, this height isn't S, because S is the slanty side. And so we're going to need something a little bit smaller, hopefully in terms of S. We could use either the Pythagorean theorem, or we could use features of 30, 60, 90 triangles to kind of fill in the information here. And I'm going to opt for the latter just because I'm well practiced with the 30, 60, 90 triangles, and I think that'll be a bit easier for me. If this side length is 2, this is 1, and this is root 3. So maybe if this is S, this will be S over 2, and this will be S times root 3 over 2. Cool. So the area for the triangle then will be 1/2 base, which is S, and then times height, which is root 3 over 2s. A little quick note, this number to me does make sense because if you tried to like find the approximate value of this fraction, it's like 0.73, I think. A little bit less than 1. And essentially this height right here is a little bit less than the slant height of the S. So that's why to me this fraction makes sense. Ultimately, the area of this triangle is going to be S squared times root 3 over 4. Cool. And this right here is going to be just the area of the triangle, and I'm calling it capital A because it'll be the same area as this blue triangle right here. So let's plug in 8 over the 4th root of 27. It's going to be a bit strange, but let's just try it out, see what happens. 8 over the 4th root of 27. We're going to square that because of this, and we're going to multiply by root 3 over 4. And now we just need to kind of settle down the algebra, or the arithmetic rather, here, and then plug it into this fraction and see if we get 7. What should we do? Maybe let's expand the square. So with fractions, you can, if you have a fraction squared, you can square the numerator and then square the denominator. And for now, I'm just going to like take the definition of squaring and just multiply that thing by itself. Although I know that if you have two fourth roots and you multiply them together, you get a square root. Like, for example, let's see, the fourth root of 16 would be 2, right? Because 2 times 2 times 2 times 2 is 16. And then if we tried to multiply two of these together, we would get the number 4. So let's write that out for a sec. Fourth root of 16 times fourth root of 16 is 4. And this number also happens to be just the square root of 16. You can prove this to yourself with exponents or other radical rules, but essentially squaring the fourth root of 27 just gives me the square root of 27. All right, and I'll keep that root 3 over 4 the same for now. I want to get these talking to each other. That's not that hard. 64 divided by 4 is going to be 16. And then I want these two talking to each other, and that'll be a little bit harder. Although I know with positive numbers, root 3 over root 27, I could actually simplify to root 3 over 27. Square roots and like multiplication and division, you can kind of distribute the root over multiplication or division. And so here, I know that this number and this number are going to be exactly the same. And that does let me simplify the fraction to 1/9. And then I can actually reapply those square roots to just the top, just the bottom, and I do get 1/3 out of this number. So these two numbers simplify to 1/3, or like a divide by 3. So this is my fraction for the area of the largest blue triangle. Let's substitute that in for A. So right here, it'll be 21 over 16 times 16 over 3. Nice. The 16s cancel, and I'm just left with 21 over 3, and that is 7. Cool. Well, that was a fun algebra, arithmetic, and geometry problem. Not too bad. Answer is 7. Let's put it right here. There we go. That's the 7. Let's check this off. These are actually equal to each other, and I'm all done. So thanks for watching, and I'll catch you tomorrow. Bye.